Assalamualaikum and a very good morning. So we are now in chapter 3, part 2, functions of combinational logic. Medium scale integration MSI allows integrated circuits to have 12 to 99 gates manufactured on one chip, and it could perform functions such as counters, shift registers, arithmetic logic circuits, encoders, decoders, multiplexers, demultiplexers, or other combinational or sequential circuits. The advantages of MSI are lower cost, higher reliability, and design simplification. An adder or summer is a digital circuit that performs addition of numbers. In computer structure or other processors, it is used in arithmetic logic units or ALU to calculate addresses and table indexes. A half adder. It accepts two binary inputs and produces two binary outputs, which are a sum bit and a carry bit, and it can only add two binary digits. So this is the logic symbol for a half adder, two inputs and two outputs. And the operation of the half adder is depicted in the truth table. There are two inputs A and B and two outputs C out and sigma. So the sum output is a 1 only if the input variables A and B are not equal. The sum can therefore be expressed as the exclusive OR of the input variables. Sum equals to A bar B plus A B bar. This is XOR, as in equation 1. And Cout can be expressed as the AND of the input variables A and B, as expressed in equation 2, which is Cout equals to A AND with B. From equation 1 and 2, the logic implementation is as shown as below. So we have the summer circuit here, adder circuit, and half adder is represented as an XOR logic with an AND circuit. The output carry is produced from the AND gate with A and B on the inputs, and the sum output is generated with an XOR gate. Now let's look at full adder. So full adder has three inputs and two outputs. The inputs are the two bits to be added plus an input carry, and the outputs are the sum and output carry. So there is an additional input there. We added input carry C in. The rest are similar to the half adder. The operation of the full adder is depicted in the truth table. So from the truth table we have here, let's look at the sum output. So we can derive this SOP term from the four ones in the sum output. And from there we can see that BC, the first term, we can collect them together. This is basically an XOR between B and C, and the other one is an XNOR between B and C. Right? So if we proceed further on, this is actually an XOR between this A, B, and C. So that sums our sum output, in which we can use two input exclusive OR gates. For the carry output, we similarly have four of these ones in the Cout, which can be translated into four SOP terms. And we figure out that we can make it simple, and by this way we can have AB plus C in and with A XOR with B. Therefore, we can use two full adder equations to perform one possible circuit, and this is the resulting circuit into our block diagram of full adder with 3 inputs. And full adder can also be implemented by using 2 half adders and 1 OR gate. So this is how we do it. It's an idea of adding A and B first, and resulting of that we'll add with C on the next stage. And C out is simply an OR circuit between the first addition and the second addition. And we have this equivalent logic symbol. It amounts to sum and also C out. Now what about parallel binary adders? An n-bit parallel adder is constructed using n full adder with 0 carry in on the LSB. For example, we have 2-bit numbers, we need 2 adders, and 4-bit numbers, we need 4 adders. So if you add up, let's say 4-bit binary numbers 1011 and 1000, we'll need 4 adders in total, and its operation is something like this: A4, A3, A2, A1, B4, B3, B2, B1, and we have some 5, some 4, some 3, some 2, and some 1. And we can use 4 full adders as shown below. So the C out of the first lowest LSB will be fed into the higher C in, and we'll get this arrangements in which we have some 5 is coming from C out. And don't forget to, for the C in of the first LSB, it should be connected to ground to give a 0 value. Right. 4-bit parallel adder, we can see that can be constructed like this. We have the LSB and MSB, and there is a logic symbol for that. We also have an actual 4-bit parallel adder in the form of integrated circuit 74LS283. It has 16 pins in total. Referring to the figure in exercise 1, what are the values of A1 to A4, B1, B4, C1, C4, and sum 1, sum 4 when A, 9 is added to 3 and B, 7 is added to 6? So let's look at A. 9 in binary is 1001, and the one here shown is the LSB, which is A1, A2, A3, and the MSB is the value 1, regarded as A4. And for the number 3, in binary it is 0011, in which this is B1, and this is B2, and MSB is 0. Then we perform this addition operation. So at first, at the LSB, we need to add a C0, which is 0, and 1 plus 1 is 0 with a carry, and that carry is C1, and 1 plus 1 is 0 with a carry, that one is C2, and 1 plus 0 is 1, and C3 is 0 because we don't have any carry from C2, and the sum 4 is 1, that means the answer is 1100, right? And C4 is 0, so we have sum 1 is 0, the summation at the higher bit, sum 2, 0, sum 3, sum 4 is 4. And if you want to expand this adder, of course the adder can add numbers which are 4-bit, but let's say we want to add more than that. So we can combine these 4-bit adders to perform higher bit addition. For example, we can combine 2 4-bit adders to create an 8-bit adder, like this. Okay, this is 4 bits and 4 bits A1 to A4. The other 4 bits is A5 to A8. So what we do to perform this 8-bit adder is we cascade 2 4-bit adders together. That means the C out from the first adder, lower adder, is fed into the C in of the higher adder. And we call this process cascading. We can see from figure A how we cascade two 4-bit adders to form an 8-bit adder. In figure B, we can see cascading 4-bit adders to form a 16-bit adder. This is using four-bit adders. For subtraction, for A minus B, we can use 2's complement. The bits of the subtrahend or B are inverted and carry in, we feed in value 1 to produce the 2's complement. That means we add 1. The design subtractor using parallel adder is shown here. So the B is inverted and CO or Cin is equals to 1 to produce the 2's complement. The rest remains the same. For ripple carry adders, the output of each adder is connected to the carry input of the next higher order stage. And we have something called the carry propagation delay. As it moves from one stage to another, let's say one addition requires 8 nanoseconds. To proceed to the next one, we will require another 8 nanoseconds, and in total we have 32 nanoseconds for a 4-bit adder. And how we eliminate this? We can use a look ahead carry adder to solve this problem. Comparators. So the basic function of a comparator is to compare the magnitudes of two binary quantities. It determines whether two numbers are equal or not. An equality can use exclusive NOR gate as a basic comparator because output is 0 if two input bits are not equal and 1 if the two input bits are equal, as shown here. To compare the equality of 2 bits binary number, we can use an additional exclusive NOR gate like this. And we add an inverter at output of each LSB or MSB. And then we use an AND circuit at the end. And if both are equal, then that means the output is equal. The number is equal to B. So in this exercise, we're trying to compare A 10 and 10 and B 11 and 10. So for A, if the first A0 and B0 is equal, the output will be 1. And for the second bit, A1 and B1, if they are equal, the output will also be 1. And if both are equal, it is ANDed together, and we have 1 as an output. For B, if both are not equal for the first bit, A0, B0, the output will be 0. And for the higher bit, even though it is equal, the AND gate will produce a 0 to indicate that the 2-bit number is not equal. So for inequality, that means not equal. Many IC comparators provide additional outputs that indicate which of the two binary numbers are being compared. If A equals to B, then that's what we did before, A equals to B. If A is greater than B, it will give another output, and if A is less than B, there will be another output pin for that. So the figure shows the logic symbol of a 4-bit comparator. So we have three outputs, A greater than B, A equals to B, and A less than B for this 4-bit number, which is fed into the comparator. So if we have A equals to 0110 and B equals to 0011, the output A greater than B is high because the value 0110, which is 6, is higher than 0011, which is 3. The other two output pins will produce a low output because they are not equal and they are not less than B. So this specific comparator is in the form of an IC which is called 74HC85. It is a 4-bit magnitude comparator. And you can look for it in the data sheet. So exercise 4, let's say we use a 74HC85 comparator. We want to compare the magnitudes of two 8-bit numbers. So how do we do this connection? Is we use a cascading input from the first 4-bit LSB to the higher 4-bit MSBs. So it shows results of something like this, which is the LSB output A greater than B, A less than B, A equals to B is connected to the MSB inputs of A greater than B, A equals to B, and A less than B. For the initial value of cascading input, we will give A equals to B 5 volts and the rest will give it a ground. So we can also design a custom comparator using logic gates. So instead of using 74HC85 or LS85, we can individually use logic gates to wire it as a comparator. And let's say we have this 2-bit comparator circuit that we want to compare whether A is greater than B or not. So the system is high, F equals to 1 when A is greater than B. So first of all, we need to complete the truth table. So if you look at this, then we will notice that each of these values will be compared A and B. And let's say A and B is equal, so it is not greater than B. F equals to 0. It will be 0 here. As we go on to each of these numbers, we'll notice that, for example, this is A equals to 1. 1 is greater than 0, thus A is greater than B. F equals to 1. And similarly for these other pins here, 1010, they are all greater than B, which is 0001. Okay, so we go up until 1111. Of course, these two numbers are equal, so and then we obtain the function of f in SOP form, which is this value of standard SOP. You have 1, 2, 3, 4, 5, 6 SOP terms, and then we simplify it using Boolean algebra or the Karnaugh map, and we'll get this equation: f equals to a1 b1 bar plus a0 b1 bar b0 bar plus a1 a0 b0 bar.